I really welcome Jeremy. He's a new member of our community and he's doing really important, tremendous scale work on systems that we are very much in need of. And key focus of his work is trying to understand the system as it natively is so that we can understand what happens when it's not working appropriately. And I do think that this is a key um, challenge. And I'm really looking forward to this presentation. Thanks, Jeremy. Let me pass it to you.
Well, Yanir, it is tremendous pleasure. I've been a big fan of NECSI for a long time, and this has always been a topic of what goes on in NECI has been very much something that I have been a fan of over the years. So it's a real pleasure to really connect here. And we're going to be talking about the internet and understanding the internet. Um, there's a lot of concern in these days. People talk about critical infrastructure. People talk about, we want to make sure our critical infrastructure is stable and reliable and all that kind of stuff. And something I sometimes tell people is like, you mean the critical infrastructure, which is the internet has now become above and beyond almost the most important critical infrastructure because all of the rest of our critical infrastructure now depends on the internet.
Yes.
Now, as a supercomputing person, a person who has managed and been involved in supercomputing community for years, the internet's a special place for us. In fact, a, a, the picture behind me is a map done in using a supercomputer 30 years ago to map out the entire internet at that time, which was essentially those red dots are supercomputing centers. So people may not know that the internet was essentially one of the main things that motivated its expansion was connecting supercomputers to each other through those white lines and then connecting it to all the people who are using supercomputing. So the internet and supercomputing have been very closely connected for many years. And so it's very natural for us to have such a strong interest in it. So with that, let me start out. I'm going to share my slides and we will begin this presentation, which is going to sort of be done in sort of four acts. So, so we're really going to try and understand the complexity of the internet here and really take an observational science approach to that. So, and observational sciences are a little bit different than, say, what we call laboratory sciences, where you can bring something into the laboratory and modify it and experiment on it. Observational sciences usually require you to kind of passively look at lots and lots of things, and your ability to do bespoke experimentation is different. I'm going to try and kind of make the argument that, understand the internet can learn a lot from observational science. So just a little bit about who we are. This work is very much a part of Professor Pentland's MIT Connection Science team, which is a scientific team that really tries to focus on problems that, simultaneously push our quest to understand things at a basic science level, but also have a practical implication. So, the human genome being a classic example. I would certainly say studying and understanding the internet, falls very much in this upper quadrant and sort of very much in line with what we try and do in MIT Connection Science. So as I said, we're going to kind of do this in four acts. So I'm going to kind of talk about four different topics here, and we're going to try sort of then pausing after each one of these topics a little bit. And, Yanir, if you can sort of maybe we'll have a little conversation after each one of them. And if the conversation becomes so engaging and we don't get to all the topics, that's okay, right? I think it's really these are conversations, and so trying to do that. So the first is I'm going to just kind of motivate why we think this is an observational domain. So first off, as I said before, the internet is really important. I think we can just assert that without evidence, additional evidence at this point. It is absolutely critical to so much of modern life these days. Um, and so therefore, it is absolutely worthy of scientific observation analysis. But I would say one of the things that's rather different about it compared to other observational sciences is this tremendous privacy concern, and that you must have the highest regard for privacy. So one of the really exciting things about the way we work in our team is that we're not afraid to have conversations with lawyers and policy people to shape our research so that we can do the research in ways that are consistent with the best guidance on privacy. And I think that's one of the keys to our progress, is that we have really incorporated that into our work, which is why we can do the observational science that we need to do. This is not new in the sense that, some of the first observations of the internet, back in the 90s led to kind of the creation of the whole field of network science, the sort of classic work by Barabasi and Albert and others, in the late 90s, and the first sort of kind of sort of complex systems measurement and understanding of the internet really sort of created this field where, and this is a classic thing, and you'll see more graphs that look like this. It just looks at every single website that they could get access to at that time, and how many links it had to other web pages. And it sort of followed this classic sort of what we call power law distribution, which is often a hallmark of a wide range of interesting complex systems. And so what's really exciting is, if just a few 100,000 observations created a whole new field of network science 30 years ago, well, today's observations are at least 1 million, if not 1 billion times larger. And that's actually been, I would say, the big challenge. Is the internet was relatively easy to observe 30 years ago. Observing it today requires a sort of a whole new sort of perspective on observational science. So one of the big things in that, the practical motivations for this observational science approach is the ability to do anomaly detection, to see things that are strange, that might need correction. And, it has been a core challenge of anomaly detection systems, is to observe the domain and develop a concept of normality. The essence of observational science is to do this, to look at a domain, understand what is typical, understand, why things are and what they typically look like, so that you can see when exceptions come along. And so this has been a great challenge to the field of trying to kind of improve the internet, is to get a concept of normality. And I would say that we have made tremendous progress in this regard, and we will certainly, share some of those results today. A precursor to that is just basic reproducibility, right? That is what science is fundamentally about, is reproducibility. When people ask me to summarize science in one word, its essence is reproducible. That is, you do not need to believe another person. The point is they can give you a set of instructions and say, if you go make these measurements and you go analyze the data you collect in this way, this is what you should see. You do not need to believe me. That is the essence of science. And so developing reproducible methodologies so that, and everything you'll see here is stuff that other people can reproduce. And this has been recognized as a high priority, and for a couple decades now, that this really should be our highest priority when understanding complex systems like the internet, is developing this reproducibility so that we can do the good observational science, which will allow us to do anomaly detection. And this is no different, if I put my other hats on, than the way we look at other domains, whether it be land, sea, undersea, air, space. They've always leaned heavily on observational science to understand what is typical, what is normal, in order to make progress. So this is kind of the sort of overarching sort of philosophical approach that we want to take here to understanding the complex system of the internet. So I am going to kind of leverage a bit of an analogy here because I know we have a very an audience with a large breadth of backgrounds here. And, we may have some people who are very um, intimately involved with cybersecurity or the internet, and we might have other people who are have a more of a science background or a complex systems background. So I'm going to kind of try and use the analogy of looking at stars in the night sky a little bit. Right. And that, that is, it leverages my background as an astrophysicist. That's my PhD is in astrophysics. And I've always just looked at the internet as really it's just a bunch of like stars in the sky that vary in their brightness, and we want to observe and understand them. And so, we have all these different stars, right? And we might color them in different ways. We might color them red, blue, and gray, just like we name the colors of the stars in the night sky to understand, what they're about. And so the fundamental observational question, which is the same as in astrophysics, is how many packets of light or how many in astronomy, how many photons, can be seen, are seen by, from one source to another. Now, we tend to have a rather preferential location here in that we mostly think about all the light that's hitting just the Earth. But for the internet, we essentially can ask the question from any location, like, well, how many photons or how many packets of information are getting between any two locations on the internet. It's no different than trying to figure this out for any two different locations in the sky. So how do we that's sort of a broad kind of, we gave sort of a sort of very sort of analogic approach. Why don't we bring in some more technical detail here? And I'm going to introduce this concept of an internet traffic matrix early because it is going to be the fundamental orienting principle for everything that we've done, right? And this is really important. It's figuring out what the proper coordinate systems are for um, for uh, for looking at any domain. And over a couple of decades, we've sort of settled on this view. So we can look at every source. So you can imagine, every single device on the internet or computer or anything can be viewed as a source of packets, or just like we could list every single star in the sky as a potential source. And then likewise, any place that it could be received is a potential destination. We sort of highlight that we anonymize this information just to kind of recognize that we are thinking about privacy from the very beginning. Um, and then from a cybersecurity perspective, we can naturally divide this space up into three areas. Our space that we may want to protect, adversary space, which is maybe where attacks come from, and then everything else, which we'll just call gray space. And the really important thing about this concept of an internet traffic matrix is it is no way limited to, say, one way of looking at the network, right? The sources and destination can be physical devices. You think phones and toasters and TVs and we are the light poles and everything that we have now that can be viewed as sources. We call this sort of the physical layer, as well as a logical layer when we actually have things like the IP addresses or the actual web name or something like that. You can apply this idea to that just as well. And then, as well as at the persona level, individual handles or identities associated with activity in social media or whatever. Whatever one of these layers we want to look at, this traffic matrix analogy applies essentially without modification. And I think this has been one of the wonderful things is we've been able to take data from different layers and model it in this sort of traffic matrix view and then go back and forth between these three layers and get the benefits of interacting with them. Again, and everything we do preserves privacy along the way in the way that, is required for the various legal things that govern this domain. So let me just pause there for a moment. Yanir, that's a lot. We've really set the stage here. And, maybe we can take a few questions
Sure.
because there's been a lot of philosophy here that's been rendered before we get into this.
Anyone who has questions, please raise your hand or just come on video and say something. But I think that this stage of the discussion really rests primarily on what Jeremy has articulated, which is this is about observations. And we're not yet talking about any representation, but the basic framework is um, this idea that what we want to do is watch what is actually happening and see if we can characterize it using systematic behavioral descriptions. Um, I don't know whether you want to say a little bit more about that correspondence. I don't know that people are really looking from every star towards every other viewpoint, which is indeed less um, of an opportunity. Um, but I think that the basic understanding of the correspondence between this and other fields of observation is important. I do think that we might ask at some point, maybe in the future, how much observation might be changed if you not only observe passively, but you actually make some changes and see how it behaves in the context of those changes. Any comments about that, as long as we have a few moments?
Well, I will say that, with respect to the first thing and the concept of, which is different here where we're kind of want to know what the sky looks like from every star, right? There's actually, though, a deeper concept there when we talk about the fundamental thing, when we talk about things like Galilean invariance and stuff, where the whole point, the fundamental assumption of, physics and science is that the laws of physics should be the same everywhere in the universe, right? That is a critical assumption. And so the when we observe the night sky, we have this assumption, well, if what is it that we would observe that if you went to any other place in the universe, we would also expect the same observations. We could convince an inhabitant of another place that, hey, we're observing this, you should also observe this. That's the exact same thing we're trying to do, right? And as we will get into later, it's like, if I say, all right, if you go and observe the internet from your vantage point and collect measurements in this way, this is what you should see, right? That's fundamentally what we're trying to get here is this sort of core concept of what invariant observation means. And I would say a great deal of science is really trying to answer that very difficult question. And so I would say that is there's a lot to unpack there, right? The concept that, and I would say generally right now, a lot of people, they kind of view there's a lot of sort of locality bias, right? Well, the way the internet looks to me is utterly unique to me, and there's no point in thinking about how what I might see would be very similar to what someone else might see. And that's kind of the challenge that we have sort of tried to address. And I think as we see later, we have made significant progress on that. So that's the first, I think, point with regards to the observational. I don't know if there's any follow-up on that in here you want to.
Oh, let's keep going. We have a couple of questions. I think we should pick one for right now, and maybe we'll get back to other ones. Um, so, can you talk more about creating something or looking for pattern emergence that is reproducible in a system that is always changing?
Yes, that is a fantastic question, and I'm glad. So there are. much of the statistical analysis of many of the observations that people did, people found very frustrating because it had the results were always just well, it's just so dynamic that there's no consistency. You measure one moment and it's completely different than the other. Well, and so a lot of folks had sort of given up. And perhaps through just ignorance or just we did not accept that. We did not accept that. And we said, well, with sufficient data, I should be able to figure out, or let's put it this way, if that's the case, I really want to know why. And so that's often, I would say, a fantastic way of dealing with a difficult problem is not to sort of just challenge and be like, if it is the case that it's so dynamic that it cannot be observed, in this way, that this assumption fails, can we show that really definitively that it is just so dynamic? And so we sort of threw the kitchen sink of analysis at it and discovered that, well, actually, if you understand the statistics in the right way, it becomes extremely stable. And we'll get into this later, but the real challenge that people were facing was that the data is all what we call heavy tail statistics. So, and the vast majority of analysis that happened before was light tail analysis, which is just so you know what light tail statistics are, is if you've taken a statistics course, unbeknownst to you, it was exclusively on light tail statistics, i.e., Gaussian, Poisson, normal distributions, the probability of rare event of large outliers is very, very low, and all of our statistical tests were very nicely. Well, it turns out there's almost no data having to do with the internet that for which that assumption is true. But if you analyze that kind of data using traditional light tail statistics, it will always seem so dynamic that you cannot analyze it. But once you understand and develop the techniques of heavy tail statistic analysis, all of a sudden it settles out. And that was our biggest thing, is we learned some practical methods to do that. And everything then just stabilized, and we saw tremendous stability over time. And so that was a great question. And probably I should go into the next part of my talk based on
Let's
that.
do that. But again, when you say stabilized, it doesn't mean the dynamic stable. It meant the description stabilized using those forms of description. Go ahead, Jerry.
Yes.
Yeah.
Yes, exactly. 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 So let me talk a little bit more about how we're actually go and get this data and observe it. And then we need observatories, we need telescopes, we need detectors. And that's actually what we call these things in the internet observatory world. We've really borrowed a lot of ideas from the astronomical community. So we can now use this picture that we created before of things that this is the way we will look at our universe in terms of this traffic matrix, and we can now imagine placing different observatories. So the first thing is what we would call endpoint observatories. So if you just start collecting the data that's hitting your computer right now, that's an endpoint observatory. And any of us can do that. And in fact, I encourage people to do that. There are tools that you can get to do this. You will be shocked at the diversity of information that is trying to talk to your computer at any given moment, right? If you just let it listen, you'll have thousands of computers that have been trying to reach out to you in the point of in within an hour, if not sooner. So it's a very dynamic environment. Obviously, presumably this Zoom call will have been the thing that sent the most data, but there's going to be a lot of other things that tried to talk to your computer, just in through routine operation. So we call those endpoint observatories. And those can be very useful, and particularly if you want to aggregate them, you can create very powerful observatories that way. We then sort of have what we call more local observatories. So let's say you're part of an organization or you are in the cloud. Your cloud provider can observe the entire cloud and everything going in and out of it, right? We would call those sort of local observatories that kind of have a sort of broader view, can see a lot more things going on. And as you can imagine, every organization that has a VPN or some kind of way of kind of defining a boundary, of course, observes that boundary very clearly. And as of course, all the cloud providers do this well. So this is information that is being collected in large quantities today. So it is absolutely happening. And then there's sort of formal wide area observatories that are really trying to kind of look at everything. They're sort of like not really servicing any particular organization other than science and trying to really just look at what's going on the internet, just trying to kind of be a weather satellite for the internet and see what's going on. So these are kind of the different perspectives that we have, and each one provides different data and can be useful in different ways. And it's also very important when you analyze the data, understand where it came from. So if the data that you will see at a wide area observatory or a local observatory or endpoint observatory, they will look very different. You have to take that into account. This is one of the ways people got sort of a little bit confused is they would compare, say, an endpoint observatory to a wide area observer and say, well, these don't look the same. It's like, no, you have to compensate for known differences in viewpoint. And this is no different than any other domain. Like where you observe from has to be taken into account in order to properly understand what you're seeing. So here's some examples of some of the prominent internet telescopes that some of the data I will talk about today. These are some things that are doing this right now. Two I will focus on particularly is CADA, which is the world's largest internet telescope. It is simply they've been doing this as an incredible service for a couple of decades of just observing about 0.5% of the internet. So they have access to what's called a dark space. So that's a space where no traffic. There are addresses on the internet that are unassigned. There's not supposed to be anything happening on them, but you can just sit back and passively listen on them. And if the internet was working perfectly, it would see nothing. It would be absolutely quiet, but it is, of course, filled with communications that are trying to communicate to these essentially empty spaces of the internet. Just as before, if you on your own computer you just let it passively listen, you would see thousands of things trying to talk to you, none of which was invited. There's just lots of things going on the internet, a lot of it not stuff that we like going on that is just sort of filling the internet. And this is sometimes called the internet background radiation. So we have the background radiation concept in cosmology. This is often referred to as the internet background radiation. There's just an enormous amount of traffic going on. So the CADA telescope has kind of been the world leader for doing that. They can collect, almost 100 trillion packets of information. And then there's a company which is called Gray Noise, which is the world's largest sort of honeypot or honey farm. So they set up computers like these endpoint connectors, but they have thousands of them, and they're trying to engage in sort of active conversations. So unlike your computer, which is mostly just denying the connection, it's saying, "Oh, you're trying to talk to me. Let's have a conversation. Let me learn about what you're interested in, and then I will try and categorize that." So it's kind of a more deeper analysis of these conversations that are attempting to take place. And this is computers that do that are often called honeypots. They're trying to actively have conversations. And if you have a lot of honeypots, those are called a honey farm. And Gray Noise is the world's sort of largest honey farm doing this. So these are two very important sources of data that we will be talking about more through this talk. So what are the photons of the internet, right? What are the discrete pieces of information that the internet is built out of? And there's these things called packets, right? So pretty much all the communication that's taking place, every single bit that's making this Zoom call happen is something called an internet a packet, an internet protocol packet. It's a very well defined format. It consists of two pieces, and the way to think about it is it's like a letter, right? It's no different than delivering a piece of mail, right? And the letter has an outside, which has information about where it was sent and where it's going and where it's coming from. That's called the header, right? And it's a very defined thing. Just like when you mail a letter, there's a particular way you want to format the address of where it's going, and the way you format the return address. And so this is the same thing. And the zip codes of the internet are essentially what we call something called the source internet protocol address and the destination internet protocol address. If you ever see numbers like 128.32.55. 144, these sort of four number things that maybe you've observed or pop up here, like numbers like this over here. Those are these zip codes, right? And they tell us essentially to first level where things came from and where things are going. And one of the things that we do that's unique is we pretty much just look at these source and destinations. That traffic matrix view, pretty much that's all it does. It cares about where things came from and where things are going. And we've discovered that you can learn an awful lot about what's happening by only looking at that information and throwing away everything else. This also helps us with privacy because these zip codes, for the most part, have to be extremely public in order for the internet to function at all. Um, it is generally people who observe the internet are pretty okay with sharing this information because every single time you send packets, like all your Zoom packets, it's being these information is being observed by dozens of companies and entities that are recording it already because they have to in order for the internet to work. So this is stuff that's already being collected. People are generally fairly comfortable with it being collected, and so we really focus on that. So then, but to take it a step further, we still want to anonymize it. There are still people like, that's great. I'll send you the source and destination IPs. I'll send you my zip codes, but I really would actually prefer to send you an anonymized version of that. And this is where this traffic matrix view really shines, right? So here's an example of a network, right? A typical network. These dots here are could be computers on the internet, and these are their zip codes. And we see here that zip code 4444 sent a message to 8888, and someone recorded that, and they want to share it so that people can analyze it, but they want to anonymize it. So they can just remap that to, I'm going to say 4444 now becomes 1111, and 8888 becomes 2222, and they can hold that mapping information. They can keep that to themselves, but this doesn't change the traffic matrix in terms of all the math we do on a traffic matrix will remain unchanged regardless about how we reorder the rows and columns. So this is a fundamental property of linear algebra and matrix mathematics, is that the computations are generally what we call invariant to permutation. And if you ever hear someone talk about something, this object on the left is sometimes called a graph, right? You might hear things about graph neural networks. That is essentially what is the defining property of a graph neural network, is that the sources are invariant to permutation. That is, it's just an invariance that you assert. And again, it's very powerful. We can represent the data this way. The person who sent the data can permute it however they want. We can still do analysis. We just don't know when we see things that are interesting, which particular one it is. Of course, if we see something very interesting, we'll often go back to whoever gave us the data and say, hey, by the way, we saw this very interesting thing associated with these two numbers. You do with it what you will, right? But we don't have to do that. We don't have to know. In addition, we often bind this with legal agreements. So it's not just that they send us anonymized data, but we have what we call a standard business data sharing agreement where it says, and we will not de-anonymize. That is, we will make no attempts to ever really figure out what these things really are. And that is sort of a fundamental part of our whole process, is it's not just anonymizing the data, but doing it in the context of a legal agreement that says, hey, we're going to do our science, but we will never attempt to de-anonymize. And that agreement is what really makes the lawyers very happy about the situation. It's not the technical anonymization aspect. It's the fact that we have an agreement that says we're only going to do this with the data and we're not going to do other things. And that combination of technical means and legal agreements is what really allows us to get the data we need to do the science. So what do we do? So what a key thing we do is we basically now we've stripped out all the other information. We just have these zip codes that are in these pairs of source and destination IPs, Internet Protocol. This is just sort of the shorthand for that. And one of the really sort of special things we do is that we collect it into just fixed buckets, right? So we typically these will be a power of two. We'll collect maybe a few 100,000 buckets, and we will always, oops, I'm sorry, we will always analyze the data in fixed bucket quantities. So we take our data and we say, all right, we're going to look at 2 to the 17, 130,000 bucket packets at a time, and we're always going to analyze it in those discrete chunks where we always have the same amount of data in the bucket. This goes directly to the question in the previous section. This is the practical discovery that we made that allows us to see the invariance in the system. Until this discovery, almost all analysis of network traffic was done with what we call fixed time windows. People would collect, say, all right, I have data for 10 minutes and I'm going to do 10-minute windows and I'm going to collect data in those 10 minutes or 1 minute or an hour or whatever. They always used fixed time buckets. The problem with heavy tail data is the fluctuations in a fixed time bucket are so enormous is that they make the data essentially look completely non-stationary. That is, you will not be able to see any patterns. And once we realize, no, if you pick a bucket size and hold it steady so that the time window changes, but the amount of the number of observations change, we then could now everything became very, very consistent because we had essentially the exact same number of statistical samples that we're analyzing. And this was essentially a key breakthrough. And, colleagues of mine who are experts in heavy tail statistics, which is, by the way, a very nascent field. I encourage people to study it. It's a very, very important field, very nascent, lots of opportunities there. Generally, there's a sense like, well, we probably could prove that that was probably the case, but those proofs have not been done yet. But it is an empirical observation at this point that whenever you're dealing with data of this nature, avoid buckets of constant time, use buckets of constant data, and then the statistics behave much, much more nicely. So we then collect these, we then anonymize them, and then we save them into these traffic matrices. And here I will get a shout out to a critical piece of technology that is called the graph BLAS. So this was 20 years ago, we realized that analyzing data of this volumes was going to be impossible with the software we had at that time and the math that we had at that time. So many of us in the math community set out to define what the key mathematical operations were. And then, based on, we wrote this up in a book. And then some industry folks came to us and said, hey, we think we could make a software standard that would do this kind of processing very fast. And that standard became the graph BLAS and has certain unique features to it in terms of analyzing this kind of data. In particular, its ability to create extremely large matrices. So I didn't mention this, but the standard addressing system of the internet allows you to have 4 billion, unique addresses. So when we first built the internet, it had 4 billion, 2 to the 32, essentially addresses. And so that's a really big matrix. 4 billion by 4 billion is larger than any other software could readily handle. And so the graph BLAS does that, which really made this possible for the first time to really analyze, data sets that are drawn from the entire internet in an incredibly efficient way. And this is the data that shows that. So for instance, we take these graph BLAS images. We essentially take these snapshots of the internet from the telescopes, and this shows us how much compression we get. So if we were just to store the raw packets, we would be able to store, a few hundred per megabyte. A typical packet is about a kilobyte, so we can't store that many. If we just looked at the headers, we'd be able to store, a few thousands. If we just looked at the source and destination IPs, we maybe get close to a million. But when we store it as this graph BLAS traffic matrix, we get phenomenal compression and we get it down to about 1 bit per packet. And so this allows us to store incredibly large corpora of this data. We get about a 3000x compression, and that directly translates into speed of analysis. So unlike pretty much all other formats for storing this data, the graph BLAS is designed to be analyzed. It's a data structure that's been created such that you can do the math on it very, very quickly. So over here, and we've done various performance measures here. It's a supercomputing person who runs a supercomputer. I have access to supercomputers. We do other people who kind of lead the world in these measurements, and kind of, this is even an old measurement now. It's even faster today. But with 1,000 server supercomputer, we could analyze 10x the American internet traffic. Right. So I can now tell you, yes, it would be absolutely possible to take snapshots of the internet and analyze it and process it in real time. And this is now a doable thing. And this is entirely because of the graph BLAS. Before this came along, both of these things would have been considered impossible. It would have been considered impossible to store, and it would have been impossible to process. And so when this technology emerged, about 6 years ago, that's when we really set out on this. So we're like, oh, well, now that we have this technology, let's actually go and do the science. We actually, for the first time. So this is just an example of how the detector technology got good enough that we could actually do the science. And that's actually how most science really advances. Someone develops a new way to measure something that can look at, a lot more of a domain and look at it much more deeply. And then all of a sudden they can do completely new science that was not possible before. So that's sort of the next pause. This just sort of sets up the instrumentation for this. And let me pause and take a few questions now from the audience.
Yeah, I do want to say we don't have a lot of time, so it would be good to see a little bit more of the actual data. Um, should we go ahead, Jeremy, or you still want to
Let's
take?
press on if we want to hit that 10 minute. I'm happy to stay beyond the 10 minute, the one,
I say
the
beyond, but why don't we press on?
why
Because
don't we press on then, and I will get to some of the highlights, right? So with that, I will I will race ahead, um, and I'm going to jump ahead and skip the mathematical interlude, right, and proceed directly to what we have seen, right? Hopefully, I've gotten you all very excited about that. So, oops. So we'll skip the mathematical interlude, which, sorry about that. If you want to know more about it, just go look up this book, Mathematics of Big Data, where we talk about all the underlying math necessary for do this. And let's talk about what we have seen. So first off, I'll just say that, when you look at a stream of data here on the right, this can be any stream of data. There's a whole bunch of quantities we can compute on it, right? And I'm not going to belabor these statistical quantities, but there are about 9 statistical quantities that you can compute on any stream of data. And the math for that lines up exactly with this graph BLAS library. So we can do everything we want. And oh, and by the way, all of it can be done on anonymized data with no limitations. So what do? We then create these pictures of the internet, these sparse images, right? And we know how to do AI on on images, don't we? Like neural network are very good in analyzing images. So we have these are just very big images. They're about a quintillion pixels. They're very sparse, but they're still very, very large. So at some level, these are the largest neural networks in the world. Quintillion, they can take quintillion pixel images. We do a bunch of sort of standard neural network types of things. But one of the things that we do that's very different than traditional cyber analysis or traditional AI is that mostly people use AI to categorize things. They train their data on a set of known things, and then they try and find those known things. Well, what we're trying to do is find the background. We're trying to find what's normal. So we use this approach to train models of what is typical and what is normal on the internet. So let me give you an example for that. So, here is a quantity we take, which is we just look at, how many unique sources do you see in a bucket of data? And we do it for different window sizes, right? And we see this pattern here. And then we discover that, oh, if we just scale this by the window size to the 1/5 power, it all lines up. And so that's an example of a model that we can develop. In fact, this works for unique sources, it works for destinations, it works for how much packets are on the internet. So what we discover is that this we can make a very strong prediction in terms of if you go and collect a certain amount of data of a certain amount of size, we can tell you how many unique sources you should expect to see. And it follows this very simple power law model of that. And so this is one of the first discoveries we made is like, oh, we don't, if I collect with one size of buckets or someone else collects with a different size of buckets, we can actually scale in between and make very strong predictions about, what they should see based on different bucket sizes. And so that's kind of one of the first really fundamental observational examples that we see. Let me skip this. So another thing that we saw is that almost all the quantities, any one of those 9 quantities tend to follow what we call a Zip-Mandelbrot distribution. This is a classic heavy tail distribution with 2 parameters, and it basically just says that, if I'm talking about, say, the number of packets coming from a source, well, most sources I will see will produce very few packets. They might produce just one packet, but a few sources will be producing an enormous amount of packets. We're experiencing this right now. If you were to listen, record what was hitting your computer, the mass majority of the sources you would see would be sending you only one packet. But this Zoom call would be sending an awful lot of packets. It would be this dot over here. And we discovered is that we could, with enough data, we could create very precise models with 3 decimal point accuracy, and that this would sort of universally fit almost any kind of quantity that we could discover that we could measure. So we sort of this universality of the Zip-Mandelbrot distribution across a wide range of quantities. We also saw that if you wanted to do the cross correlation of sources, so for instance, if I have one sensor, right, and it observes a source of a certain brightness, what is the probability of seeing at a different source? So we look at the K telescope, we measure a source, and then we say, what's the probability of seeing it in the gray noise data set? And we see that it follows a very standard sort of logarithmic thing that the probability of seeing it goes with a log of the brightness up to a threshold at which point you will always see it. I should say that gray noise does categorize data as benign and malicious. And then we saw a very interesting effect that malicious traffic tends to self-limit itself. So, all the sources, including the benign ones, kind of follow this curve here. But if we just look at malicious sources, they tend to not want to be so bright. There's a certain brightness they want to achieve, and then they will throttle themselves so that they aren't too bright, so that they don't get detected. And so this sort of becomes now a signature that one can use. This is an anomaly, right? Malicious traffic looking different than typical traffic, right? If it sort of self-limits itself, that might be an indication that's something that is bad. And this is an example of how you can use it, background models and anomaly detection to actually do useful things. Another thing that we observed was what we call the self-correlations, right? That is, you can go on your own computer and measure who talked to me. And then I can ask the question, if I saw someone talk to me right now, what's the probability that I will see them talking to me, an hour, a day, a year from now? And what we saw is that benign sources have a very long half-life. And in fact, it follows this thing called the modified Cauchy distribution very, very well. We can fit parameters to it very closely. But the nice thing is benign sources aren't trying to hide. If a benign source reaches out and talks to your computer, there's a good chance that if you would have to wait 4 years before the probability of it trying to reach out and talk to your computer again decayed by half, right? Versus malicious sources where it can be a few minutes, right? You can see it, if you see it, the probability that you'll see it again drops by half in under 30 minutes. So again, this is another way in which these background models can help us see benign versus malicious traffic and be kind of a great way to use anomaly detection in this way to see things. And it's just kind of it's an obvious in retrospect. Malicious things are trying to hide. They're not trying to be seen. And that act of not trying to be seen can be a signature for, finding these things. And in fact, we even have sort of another analogy of this is even like, well, what geometric analogy would allow us to kind of understand this behavior? A way to think about it is as sort of as orbits, right? So you can think about sort of high flying satellites in geostationary orbit. They're always sitting above you. They don't move very much. You'll see them every night for years before they drift versus a very low flying rocket. And this sort of model corresponds fairly nicely to what we've seen in that the benign traffic very much it sort of orbits you in this sort of very high, almost geostationary orbit around you, if this is you in the middle, versus malicious things, which tend to fly overhead very quickly. And if you see them once, you're probably not going to see it ever again. And it's on a very sort of different type of orbit. So, with all of this, I will sort of wrap up here with we now have a holistic model of the internet background. That is, if you deploy a sensor and you collect a certain number of packets and you see a source emitting D packets, you can ask the question, what's the probability at a later time t being seen by a different observer? And it's now this basically relatively low dimensional 5 parameter model that is essentially the model of what you can expect to see on the internet. Now, I will say that these parameters do change by location, as you would expect. So a different location will have different parameters for this model, but these parameters actually do not change much over time. Once you measure them once, they tend to be very stable over months or even years. And so with this, we're able to actually have, for the first time, a true observational science model of what is normal on the internet that we can now have other people go and test. And, so that will bring me to the end of my talk, and I'm happy to engage in further conversation. Thank you very much.
Thank you, Jeremy. Very, very interesting. Both the general framework for doing the analysis, but also, of course, some of the specific results that are providing some insight into what's going on and in the internet. So, other questions, please. Who has some questions?
I see there are a
Um,
couple of questions in the chat.
okay. So we talked about a little bit about the patterns that are detected. Curious about to what extent this allows us to understand diffusion of bots and more sophisticated agents across the internet. Do you have anything to say about bots?
So, um, first of all, um, bots obviously play a huge role in the random, unsolicited traffic that is a large part of a lot of the data that we see. And this allows us to separate those bots from good bots and bad bots, right? So those that benign is mostly what we call good bots. There are good bots out there. You think like Google, it is has a bot army to scrape the internet and see things. And so it allows us to separate the good and bad bots. And then once we've identified the bad bots, we can further group them by their behavior into sort of distinct families of bots. which can then be used to determine, do we want to do anything about them, right? Where are these bots coming from? Who's letting these bots through, right? A lot of these bots use methods that, through relatively routine things that already exist in the equipment today could be stopped and be turned off. And this allows us to take that information to the folks who would do that and actually stop it. So yes, we can. That is definitely a goal, is to use these things to, make it clear which things are doing things that seem to be helping the internet and which things that may be doing things that are not helping the internet and making are problems for the internet.
Since we already had a question about bots and their relationship to bad actors, maybe you would like to answer this question. What about bad act political bad actors? And I don't know which ones you want to identify or not to identify, but the question is particularly asking about Russia and China trying to skew information highway. So the question is, what about political actors that are trying to change the messaging on the internet?
Well, I think that, and then that works like several layers up in this pyramid, right? Which the stuff is, we absolutely look at those kind of things. I think one of the most important things that we should be able to do with this is sort of, it has been considered attribution has been considered an impossible dream in the internet for a long time, right? Part of the reason this stuff happens is that there's this sort of sense of anonymity, right? That people can just pose as anything. And I think that once you see structures, right, and you can say, like, for instance, let's talk about how an influence campaign typically works, right? So typically, there's someone who is, quote, a legitimate person who says something that someone else wants to promote, right? It advocates a particular agenda item, right? And that thing may be true, it may be false, whatever, but someone else wants to emphasize that, right? Um, the what happens then is, and this is no different, and again, there's a big gray zone here in terms of there's lots of people who just want to sell products and they want to move this. So the technology is sort of agnostic to the purpose. There's people who want to legitimately promote things, and there's people who want to just sort of promote things in an illegitimate manner. Well, the main way you do this is through upvoting. That is, you have lots and lots of other bots that are compromised accounts. Let's say you were on a social media account and they had billions of accounts, and maybe you had indirect access or control of several hundred thousand of them. The person who has it doesn't know that they also have that their account has been compromised. Well, with relatively very, very subtle upvoting of a particular thing from a very small percentage of that, you can have a dramatic impact on making a certain idea rise up. And it can be as small as thousands, right? Well, these upvoting patterns are very artificial. In fact, you can witness them if you join some forum that has hyperbolic material on it. You'll often see very unusual upvoting patterns. Someone will post something, and then within a few minutes, there'll be 999 upvotes. And then a comment that gets upvoted by 997, and then another comment that gets upvoted by 995. And this happens within minutes. Well, that's obviously defies reality. That's not possible. And so these kind of things. And so one of the things we've discovered, and this has been a whole nother part of our work, is that causality is a very fundamental truth. And if two things happened at nearly the same time, it implies that there must be some coordinating thing, even if you don't observe the coordinating event. And so we've made significant progress in basically being able to uncover networks just by the coeval activity itself. And so this allows you to say, well, you know what? These things are clearly engaged in coordinated activity. You can label them such just because it would be causally impossible for this statistical pattern to emerge unless there was a hidden, correlation. And causality is just a very, very fundamental truth. And so that can be a big way that we can sort of work on discovering these things in the what we call more the information sphere.
Let's take two more questions. One is,
Can
uh,
I ask a related question?
yes, go ahead, Marcus.
Oh, thank you very much. Um, I was wondering about, the hierarchy structure in the internet related to what you just outlined. Um, one of the big promises of the internet was always that it would foster more democratic interactions because it's there for everybody at the same time. You just need a basic server and you can interact with everybody and so on. So my question is, if you are a bad actor in the sense we just described, of course you want to somehow funnel or channel the information through your activity at least. It might not be a physical server, but you want to concentrate action and you want to have some action that everybody else then would notice. I mean, that's more or less, I think, in my words, what you described. So, did you see in your data some trends in, that over the years the internet evolved, that it became in maybe in different measures, which I can just hand waving now, that it has become a bit more hierarchical in that sense?
So, no. So
No.
our data is we've mostly focused on data in the last several years, right? We have not done although we have data that goes back a couple of decades, we've been more focused on, there tends to be in this field a bit of a recency bias. People really are more concerned about what's happening now. And so we've tended to more focus on the ability to process and understand what's happening now than the historical trends. I mean, we of course did see a shift in the pandemic that was rather noticeable. In
Mm,
particular, um, the many of the kind of bad actors who use botnets to do stuff um, on the internet, they as I said, they rate limit themselves based on internet
mm,
volume. So they always want to be a certain percentage, not above a certain percentage. Well, when we shifted in the pandemic to just the amount of traffic increased dramatically, well, their activity increased just exactly in proportion to that. And sort of this proved for us that yes, they're clearly engaged in an automatic rate limiting process. And so as the internet went up and a lot of people observed this too, but we certainly observed that when the pandemic hit, literally you could show when the pandemic hit because the activity of these things happened. And it clearly shows it was an atomic system. It's not someone went around who was like, "Oh, I'm measuring the internet and now I'm going to increase my botnet." They are making measurements of the internet and making sure they're sitting at certain thresholds. So when the overall traffic goes up,
mm,
they can do that. So that's one example of what we saw. I mean, I'd say an interesting thing that we saw is that there's this thing called noise storms.
mhm,
So every 6 months or so, there is these essentially someone, sends 10,000 fake packets to pretty much everyone on the internet,
mm, mm, mm,
and I can, explain why you may or may not want to do this, but, that's something that no one had ever really observed before, that this every few months, this thing is occurring. Right. And we could, analyze it and show that it was clearly mechanical. It was a statistical thing. It was not due to, configuration areas. So that's an example of, so let's put it this way. In my career, I was very interested in those structural things when I started off in this space about, the nice things we do in graph theory and the little pictures we draw. And over time, I moved from a strict structuralist to a strict temporalist, which is that the
mm,
structure is actually relatively uninteresting. It's just stars everywhere. But the temporal behavior and what's happening temporally is very interesting. And that's where all the interesting things happen is the way these things fluctuate over time. And so I've less focusing on the traditional topological hierarchy and more focused on the temporal fluctuations is kind of where we've seen the most interesting phenomena.
But if you are interested in temporal fluctuations, I understand your argument. I guess from a graph theoretic point of view, the internet is well also very much shifting all the time. So the architecture is not very clearly defined, I would say. But if you are interested in statistics or in causal relationship, I mean, then do you use some difference between, the typical statistical approach? So there is a causal relationship, and there are methods to establish this a little bit more precisely, and just things that happen to be close to each other, but uncorrelated or unrelated, I should say. Mm,
Well, one of the wonderful things is when you build an instrument that can gather a million or a billion times more data than anyone else, or be able to analyze data on scales than no one else, the uh, the threshold detection algorithms are rather trivial. Like when you're the
mm,
first people to see something, right? It doesn't require very sophisticated things because we're seeing things that are like deviations from the background that are factors of thousands. So you don't
mm,
need, so we've tended to focus on these incredibly huge signals that no one has ever seen before,
mm,
and do that. And then, of course, as those things get addressed, and then we get closer and closer to kind of the thresholds, then it requires being more sophisticated. But we've been blessed so far in that pretty much we haven't need very sophisticated techniques. It's like, yeah, there's 1,000x increase and it happened for one day and then it disappeared. You
So,
know, I don't need to be a very sophisticated AI to say that might be something that we might want to investigate.
so one of the important things that we might close on is that given the fact that we have this tremendous telescope to observe the internet or microscope or whatever you want to call it, scope, um, the driving issue often is what questions do we ask of it? And so I do think that from the point of view of the community, it might be incredible. Maybe people would like to send notes about the questions they would like to ask. And we can open, everyone here has our email contact. So if you want, you can send it to our institutional address, programs@nexi.edu, or to mine. I'm sure Jeremy's is also public. And you can send us notes about what questions you think this scope should be investigating, and that might give some new impetus to important research and important findings.